What is a vector? A vector is a quantity that has both a magnitude and a direction. Okay, so first of all, notice the term quantity here. A vector is a quantity just like any other quantity. How much milk do you want to drink? How much food do you want to eat? How much money do you have? Those are all quantities. However, those quantities, the ones we're most familiar with, like how much do you weigh, for example, those are called scalars. Those quantities are called scalars. But a vector is a special type of quantity that requires you to specify both a magnitude and a direction that are both associated with that quantity. So, for example, velocity is a vector. Now, yes, we do, in a lot of situations, express speeds as magnitudes or scalars. If you got a speeding ticket, how fast were you going? 70 miles per hour. You just give a magnitude. And a lot of times we use the term velocity and just treat it like it's not a vector, like it's just a magnitude. However, from a technical engineering and physics standpoint, if you're just specifying the magnitude of a velocity, then you're expressing the speed of something. The car ran a red light at what speed? 80 miles per hour. But when you're referring to velocity, you're referring to a vector. From a technical engineering and physics perspective, velocity is a vector. So if I asked the question, what is the velocity of this vehicle? Then I could say it's 40 miles per hour northeast. And that was a vector. I just stated a velocity vector. And so the first thing I want to point out about vectors is that try not to overcomplicate what it is. It's just as simple as if someone asks you the quantity of speed of something, you might say 70 miles per hour. Well, if you're asked for a quantity of velocity, then that's referring to a vector. You're just going to say a magnitude and a direction. That's it. Force is a vector. Now, yes, sometimes in casual conversation, only the magnitudes of forces are discussed, like in a boxing match. If someone gets punched, how hard did they get punched, with what force? 100 pounds, and so it's just given a magnitude there. But from a technical physics and engineering perspective, force is a vector. So if I asked the question, with what force is this man pushing on the wall? So I guess what's the force in each of these hands here? Then since force is a vector, well, I need to specify that with each hand he's pushing with a force of 50 pounds to the left or to the west. Okay, now, in general, if you ask yourself the question, what is a vector? Maybe you search this question on Google or YouTube, or you ask somebody at school. The first thing that's presented to you is typically something like this. Okay, we've got an arrow here and a bolded letter given as a symbol for the vector. Okay, now, this answer is not wrong. It's completely fine. In fact, for pretty much this entire playlist, we're going to be learning about vectors, how to add, subtract, multiply, divide, just represent vectors with arrows just like this. However, in this video where we're trying to understand exactly what a vector is, it's going to be immensely helpful for you if we view the meaning of a vector from a different perspective. And viewing the meaning of vectors from this perspective is also going to help clear a lot of confusion that you're naturally going to have regarding questions like, is the tail of a vector always at the origin? Or where do you put the tail or the head of a vector? Or how is it possible that, like in real life, you can add vectors head to tail? So if we really look at vectors from the viewpoint of their precise meaning, then you're going to see that questions like this are kind of silly. Okay, so here's what I mean. So technically, this right here is not a vector. Again, this is not a vector. This is an arrow on a page. What this is a very popular, and for good reason, graphical representation of a vector. So if you go outside and observe cars on the road, and you think about the velocity vectors associated with those cars, you don't see arrows floating around, right? Okay, but this is a very useful graphical representation for a vector, because what you can think about, so let me give you a sense of 3D space. So imagine we're in 3D space here, because this arrow here has a length to it, right? And so what I could do is I could give you a scale, like a scale on a map. So I could say, so let's say this scale is in meters per second. So this distance, this physical distance in 3D space in any direction, corresponds to meters per second. So if I take a ruler, it's about an inch. So each inch in any direction in 3D space corresponds to 1 meter per second. So what I could do is I could take the ruler, come to the vector, and measure its length. Again, maybe this vector is, it comes to the right, goes into the page, and then up. Okay, but I can measure its length and get the magnitude of the velocity. But what's great about this graphical representation is that inherently intertwined with that magnitude of velocity is a direction of that velocity. And so again, that's why this is a very useful graphical representation of a vector, an arrow in space. Okay, now let's just think about if we were going to try and make like a sort of parallel graphical representation for a scalar, parallel to what we've done here with a vector, with an arrow. What could we do? Well, okay, we could think about, maybe we could have something like a circle, and so we could measure the diameter of the circle, and then also provide a scale, and say that, so let's say this goes from 0 to 3,000 pounds. This is in pounds, so okay, so that's about 120 millimeters. So about 25 pounds for every millimeter. And this is about 6 millimeters in diameter. So this would correspond to about 150 pounds. And we could give it its own symbol as well, maybe like a non-bolded W for weight. Okay, but the idea is that this has a magnitude, but there's no direction to it. Okay, so again, this is a scalar, like a temperature is a scalar. There's no direction to temperature. It's just a number. Time is a scalar. It's just a magnitude. Okay, but now there's no actual popular use of representing a scalar graphically this way, because it's not as intuitive as an arrow is for a vector. We don't need this graphical representation in actuality. But I'm going to use it here to illustrate a point. Okay, so saying that this here is a vector would be like saying that this dot here is a scalar, right? So acting like this actual physical dot is a scalar or a weight of something would be kind of silly, right? And so it's the same idea if you talk about this arrow here like it's actually a vector. And so why am I emphasizing this? Because what you're going to learn by the end of this video is that asking questions like, where does the tail of the vector go? Where does the head of the vector go? Is the vector's tail always at the origin? Are kind of silly questions, because what you're inherently doing is you're mixing up the physical reality of what a vector is with its graphical representation. Okay, now, the next point that I want to make, and this point is really helpful to keep in mind when you start getting confused about what a vector is and how to operate with a vector arrow like this, is that, so, okay, remember that a vector is a quantity just like a scalar is a quantity. They're both just simply quantities. And so what I mean by that is when we think about scalars, okay, like the temperature of something, the mass of something, the time on a stopwatch or whatever, I think we inherently approach scalars as simple. They're just these these basic descriptors in terms of magnitude of something. They're not that complicated, okay? A vector is a very simple quantity, just like a scalar is, just a smidge more complex because it has a direction to it. It has a magnitude and a direction. But it's not that much more complex at all. So what I mean is that, so you and I could be standing outside and you want to assign a weight to something, let's say some person. And so this represents 150 pounds. And so you assign this weight, this scalar, to this person, right? That makes sense. But you could do the exact same thing with a vector quantity. I could ask you, what is the velocity of this vehicle? Well, you know that velocity is I'm asking for a vector quantity. And so you could, just like you gave me a weight, you could give me a velocity. And you could assign a vector to that vehicle. But what you really want to notice here is that the simplicity of the scalar and the vector as just these quantities are extremely similar, with the vector just being a little bit more complex because it has a direction associated with it as well as a magnitude. Both are just these quantities you're assigning to something as a descriptor. Okay, and so now with that in mind, if I started asking you questions about these graphical representations, okay, like for example, well, what does the head of the vector mean, or the tail of the vector mean, or where do you put the tail of the vector, or is the vector's tail always at the origin? Okay, well, let's first look at this from the perspective of the scalar. If you told me someone's weight, okay, and I asked you, well, what happens to what's the physical reality of when you change the diameter of the weight dot? What would you think? Well, you would kind of shake your head and be like, well, change the diameter of the weight dot, so like change the man's weight? It sounds like you're acting like the dot, the graphical dot that we used for the scalar is an actual part of the man's weight. That's kind of a silly question. Okay, and then if I asked you, well, where did you put the weight dot on the man? What happens if you change the position of the weight dot on the man? Again, you would kind of shake your head and say, it's just his weight. It's just a quantity describing the man's weight. And I mean, I put it on his center of mass because I guess that would be the most descriptive to the person viewing the graphical illustration. If it's not that complicated of a graph, maybe I could have just put the dot right here to indicate the man's weight. But if there's a lot of stuff going on, if it's a complex problem with all kind of stuff going on, then it's probably better to just put the weight at like the standard procedure would be to put the weight at the man's center of mass. But again, you would still kind of shake your head and say, but it's like you're talking about these graphical descriptions like they're actual physical reality. There's no such thing in reality as a diameter of a dot associated with a scalar. Okay? And it's the exact same idea when it comes to a vector. Remember, a vector is just a simple quantity, just like a scalar is, to describe a phenomena. If I asked you, okay, well, with the velocity of the vehicle, where does the vector head go? Where does the vector tail go? What happens to the car's velocity when you put the head at the vector head at the center of mass or the tail? You would once again shake your head and say, what head and tail? That's just an arrow. A vector doesn't have in reality, a head or a tail. You would say, well, I mean, I guess a good practice would be that you put the tail of the vector at the most descriptive point. So I put this vector, the tail, on the car's center of mass because this vector was describing the car's motion as a rigid body. So if I put the vector off of the center of mass, that might suggest that the car is spinning about its axis when it's not. But as far as do I put the head of the arrow or the tail of the arrow at the point of interest, I guess it doesn't matter, but maybe you could make it common practice to just put the tail at the point of interest every time. Okay, now let's think about the question of that commonly comes up with graphical vectors, and that is the tail of a vector arrow always fixed at the origin? That's a common question, right? Does a vector always have to be fixed at the origin like this? Okay, the answer to that question is, from one perspective, absolutely not, but from another perspective, absolutely yes. Now, I know that might sound confusing, but this will make perfect sense in a second. Okay, from the absolutely not perspective, meaning that a graphical vector arrow in general is not fixed anywhere. Okay, what we're talking about in that sense is when you're looking at vectors and scalars as just these simple quantities, right? In complete general, so there's one scalar. Let me get another scalar. There's a temperature scalar, and there's a force vector. In complete general, let's start with scalars. Are scalars fixed anywhere? Well, of course not. They're just quantities. I can assign a temperature to anything I want. It's just floating. It goes wherever I want it to go. In general, I'm never restricted to assign a temperature to something, to certain regions of space, ever. Okay, and so once again, since vectors are just simple quantities, just like scalars, they're free to go wherever you want. You can assign them to anything you want. They're not fixed anywhere. Okay, but now what about the absolutely yes perspective, that a vector is fixed at the origin? Okay, that perspective, what we're talking about there is that, okay, here's a graphical representation of a vector. I can upgrade this graphical representation this way. Okay, so this looks a lot more complicated, but all we've done is just add a coordinate system around this to aid in showing what the direction of the vector is. So let me make this a little bit smaller. Okay, this coordinate system here, you can think about, that's the vector space of this vector. Every vector is in its own vector space. When you think about the meaning of a vector from a pure algebra sense, every vector is in its own vector space. And graphically, those vectors are arrows with their tails always fixed at the origin. The vectors that we use in physics and engineering are absolutely algebraic vectors by the strictest sense. Okay, in the vector space of a given vector, so even this vector has its own vector space, you can think about that. That's like its own world outside of the actual space that we're working in. So you can see, for example, these axes are velocity in the x, velocity in the z, velocity in the y, force in the x, force in the y, force in the z. You can think of the coordinate system associated with a vector in its vector space as just part of the definition of a vector. Now, the issue with this is that it can create confusion, is that when you start adding complexities like this, then it's easy to forget about the fact that vectors are still just simple quantities in the same way that scalars are. Okay, and so to illustrate that, we can think about that hypothetically we could put a coordinate system around these scalars with these dots at the origin of the coordinate system. The only problem is that there's no direction associated with a scalar, so why do you need a coordinate system? But we could hypothetically do that. And so from that sense, if we were asked the question, are the scalar dots, do they have to be fixed at the origin of their coordinate system? Once again, you would shake your head and say, that question is kind of silly. You would think, well, how could they not be? What would that even mean? It's the same idea if you ask, does the arrow of a graphical vector have to be fixed at the origin of its vector space? How could it not be? What would that even mean? If you had a vector that was in the velocity vector space that was out here. So what does that even mean? Like the tail is not even at 0, 0. That doesn't make any sense. Okay, and so when you think about the general idea of the definition of a vector as having its tail always fixed at the origin, then you're thinking about a vector as a quantity, just like you think of a scalar as a quantity that's free to go anywhere, free to be assigned to anything. But you're thinking about that vector when you're assigning it to something as it's in its own vector space fixed at the origin of its vector space, like this. Okay, but this still can be a little bit confusing in the sense that, but like these vectors here aren't fixed to this origin. Their tails aren't. I mean, I guess they could be, but they're not. So like, what does that mean in this context? Are vectors allowed to have any interaction with a coordinate system outside of their own coordinate system? You know, we see vector fields all the time. Here's wind velocity vectors mapped over a region of the continental United States. Well, these are off whatever the origin would be here. What does that mean? Right, here's wind velocity vectors for a hurricane. Well, these are all off wherever the origin might be. What does that mean? What interaction do these vectors have with like, the origin of the coordinate system of the system? Okay, well, the answer to that question is it's the same interaction that these scalars have with the origin of a coordinate system. So let's say this is a, x, y, z. We've got some system here, and this is the origin, right? Maybe this is the weight of the man. This is the temperature of something, etc. This is the weight of the man. You've got this vehicle here. It's got a velocity vector. Put that back. The force vector is just doing something, and then maybe you assign this temperature scalar to this vehicle. It's at the center of mass of the vehicle. Okay, so how do scalars interact with like an origin? Well, it's through scalar functions. So this weight could be a function of x, y, and z, a function of its position. You input an x, y, and z, maybe a time or whatever, and what gets output is a scalar. Same thing with this temperature. But you can do the exact same thing with vectors. That's what a vector-valued function is. You have scalar-valued functions or scalar functions, and then there's vector-valued functions. You input whatever, in this case it would be like a x, y, z position, maybe a time, and it spits out a vector. This force here, this force vector, could be a function of x, y, and z. Same thing with this vector. But the idea of saying that, well, in that case, the inherent mathematical algebraic vector itself doesn't have its tail fixed at the origin would be like saying that this weight here doesn't have its dot fixed at the origin. It doesn't make any sense. Okay, so now you should have a much better sense for what exactly a vector is. There's still more for us to unpack in this playlist. More aspects that I think you'll find confusing about how exactly vectors work, actual physical vectors in real life versus their graphical arrow representation. So for example, we could take this vector here, and we could actually use its position relative to this coordinate system to find the components of the velocity in each of these directions. So let's say it's doing something like that. Well, if you measured the percent of this distance, so distance relative to this coordinate system, the percent of this distance here relative to the actual vector length, the percent distance here and the percent distance here, that would all correspond to the actual velocity in the x, y, and z directions. You take this percent multiplied by the actual velocity magnitude, and that would give you the velocity in the x direction. But in that sense, isn't the vector now intimately interacting with a coordinate system outside of its own vector space coordinate system? How is that happening? Right? I thought like the coordinates of the vector were in their own little world. How could the vector be like interacting with this coordinate system that way? These types of questions we're going to unpack as we progress through the videos. But one thing you can think about is that it's still always going to be important for you to distinguish between the graphical representation of a vector and the actual physical vector phenomena itself. But that being said, we still do need to be clear on how to work with graphical vectors. Okay, another question is, well, do vectors always have to be based on something like from physics that's always interacting with space around us? So like, could you have like a vector from something in business, like a price vector? And you would think that you could, because as you know, we use 3D space as a visual aid for analyzing relationships between variables, even if those variables have nothing to actually do with 3D space. So we could put cost on this axis, price on this axis, and revenue on this axis, right? But since we're in 3D space, again, what's confusing is that these business terms have nothing to actually do with 3D space, but we're using 3D space as a visual aid. In that sense, we can still think about the idea of having an arrow, something with magnitude and quote unquote direction, even though the idea of a direction in terms of price, cost, revenue, etc., doesn't really mean anything. So, but again, we'll unpack these ideas as the course progresses.